How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for detection of radioactivity and energy changes in nuclear reactions. So number one, what device detects radioactive emissions by converting them to light? It is the scintillation counter. Right? Scintillation is the process by which light will get emitted. So a scintillation counter is counting how many times that happens. Why is that happening? Because we have radioactive emissions interacting with it, and then it gives off light. You count how many times that happens, that's how many radioactive emissions were there. All right, number two, the mass of a proton and the mass of a neutron are this many grams and that many grams respectively. What is the nuclear binding energy for the nucleus of iron 56 if its mass is this many grams? So if you know one equation, one fancy science equation, it's probably this, equals mc squared. And it's saying that energy and mass are really the same thing in different forms. If you have some energy, you can turn it into mass. If you have some mass, you can turn it into some energy. And if we take a look at the mass of the parts in a nucleus, if you take, hey, this many protons should have a mass of this many neutrons should have a mass of this. So the whole nucleus should have a certain mass. But actually, when you compare it to the actual mass of the nucleus, you see that the mass of the nucleus is actually less than the mass of all the parts. And why is that? Because some of the mass was converted into energy. Well, how much mass? Well, that difference, the mass of the parts minus the mass of the nucleus, equals what we call your mass defect. It's how much defected, how much is no longer there. So if you take your mass defect and you plug it into the E equals mc squared, that'll tell you how much energy was created or released. So let's do this, right? We have energy equals mass, but our mass is going to be the actual mass defect. So the mass of the nucleus, actually I gotta do the mass of the parts first. So how many protons are there if I have iron 56? Well, the atomic number for iron is 26. So we have 26 times the mass of each proton, 1.673 times 10 to the negative 24, plus the mass of all the neutrons. Well, if the mass is 56 total and the charge is 26, I know I have 30 neutrons, times the mass of each one of those is 1.675 times 10 to the negative 24 grams. And then I subtract that, or subtract from it, the mass of the actual nucleus, which is 9.289 times 10 to the 23, negative 23 grams. That is going to be my mass defect in grams. And then I still have to times that by the speed of light squared. So the speed of light is at like 3.0 times 10 to the 8th meters per second. And that is getting squared. Now, another thing to watch out for is this mass is in grams, but we need it in kilograms. So I'm really going to divide each of these by 1,000. So that I have my mass in kilograms. So what I'm going to do is I'm going to cheat, and I'm just going to change this exponent from 24 to 27. So negative 27 kilograms. Because that's what happens when you divide things by 1,000. They go down by 3. All right. So now I can pick up my handy dandy calculator and I can plug and chug. And now that I'm using kilograms and meters per second, I will end up with an answer in joules. So I end up with 7.72 times 10 to the 11 joules. And that is what we call the binding energy. All right, number 3. He4 can be formed by the fusion of two H2 atoms. The total energy released is that many joules. What is the total change in mass for this nuclear reaction? So again, we're using that E equals mc squared, but this time we're solving for mass. So I get mass equals E divided by the speed of light squared. So the energy, they say, is 3.83 times 10 to the minus 12 joules divided by the speed of light squared. So 3.0 times 10 to the 8th squared meters per second. And when I plug and chug and do all that, I end up with 4.26 times 10 to the negative 29 kilograms. All right, number 4. What is the total amount of mass that's converted into energy when 4 grams of C11 decays if the energy released by the decay of C11 to B11 is 2.87 times 10 to the 11 joules per mole. So let's go again. E equals mc squared. And what are we asked to solve for? It looks like we're being asked to solve for mass again. So I get my mass is equal to the energy divided by c squared. So the energy, they said, is 2.87 times 10 to the 11 joules per mole divided by 3.0 times 10 to the 8 meters per second, which gets squared. And when I plug and chug, and beep bop, boop, I end up with, did they ask for grams? No. Okay, so you end up with 1.16 times 10 to the minus 6 kilograms. All right. I think that's it for that section. Hope you found it helpful. See you in class. Goodbye.